Okay, so in this section we're going to talk about the kind of reverse of an engine, which is a refrigerator or a heat pump. So the first thing to point out about these things is that heat pumps or refrigerators, I'll use the terms interchangeably, heat pumps are like engines running in reverse. Running in reverse. And what do I mean by that? So remember the kind of cartoon that I drew of an engine, which was a device which kind of took heat from a hot place, fed it into a device, dumped some amount of heat into a cold reservoir or a cold sink, and then in the process did some amount of work. Okay. Well, imagine I draw a schematic of a refrigerator, or an air conditioner for that matter, which is some device, so my AC unit, which I use a certain amount of electricity to run that air conditioner. What does it do? It takes some amount of heat from my room. It takes some amount of heat from this room, and it goes ahead and dumps it out into some exhaust, right? Exhaust. Dumps some amount of heat out there. And usually an air conditioner, spits that hot air into the outside world, right? Outside of your house anyway. And you can see that, if I just move these boxes around, it's kind of like I just change the direction of all of these arrows. So instead of taking heat from a hot source, dumping some to a cold source, and doing some work, here I'm doing some work on the device, and somehow I'm then taking heat from a cold source and dumping it into a hot source, right? So refrigerators, in some sense, are just like engines running backwards. And so one way that we could think about building a refrigerator is just to kind of systematically walk backwards through each of the steps we outlined when we were talking about the pressure volume cycle that we put our ideal gas piston through, right? And just like for a engine where we had efficiency, you can define the performance of any kind of idealized representation of a refrigerator. You can define the performance, and I'm going to use this Greek letter omega, kind of doesn't matter what letter I use, as the ratio of, well, how much heat do you take out of your room, out of your cold source, relative to the amount of work you had to do in order to do that, right? And by the conservation of energy, this is the same as the amount of heat you pump out of the room, divided by the difference between the amount of heat going into the exhaust and the amount of heat coming out of your room. That's just a rewriting of what the work is, right? And since a heat pump is just an engine running in reverse, it probably shouldn't surprise you that the maximum performance of these refrigerators, no matter how well you do the engineering, no matter what what you use to run them, is determined by the differences in temperatures that you're trying to maintain, right? So it's easy to be efficient or very performant if the temperature difference you're trying to maintain is very small, but it takes more and more energy, even with the same system, to keep your room a lot colder than the outside. So this maximum performance is given by this ratio of the cold temperature relative to the difference between the hot temperature and the cold temperature. Okay. And again, there are many different cycles that we could use to run a refrigerator. And one of the things that I wanted to talk about is not just running an ideal gas piston in reverse, which is secretly pretty close to how combustion engines work, but instead talking about how the refrigerator in your kitchen works. And to do that, I need to talk a little bit first about what goes on when a substance changes phase from solids to liquids to gases. So this is phase changes in solids, liquids, and gases. And this covers some of the material in, I think it's chapter 8 of the Bloomfield textbook that we skipped over. That we skipped over at the time. Actually, chapter 7 of the Bloomfield textbook, sorry. But now we're kind of coming back to it. Okay, so, great. So we've already talked in this class that the difference between the properties of a substance when it has different phases, whether it's a solid or liquid or gas, ultimately comes from the differences in the microscopic arrangements of that same set of particles, right? So for instance, ice, water, and steam, these are all just collections of H2O. Collections of, two hydrogens and oxygens bound together. And the only differences are how those H2O molecules are arranged, right? So in an ice, you have this beautiful, highly symmetrical crystalline structure, right? Every single molecule precisely in its place. Beautiful. In water, the molecules are disordered, but occupying a definite volume. Occupying a definite volume. And in steam, they're disordered and just filling up space randomly. Disordered and filling up the available space. Okay, and I want to think about this a little bit more, right? So first, when steam molecules are just flying around, through the air, high velocities, even though they're very small, they actually have a fair amount of chemical potential energy. So you remember when we talked about the burning log, and we said, well, the amount of chemical potential energy when the molecules, the cellulose molecules in wood were bound together was some value. And when those molecules were able to bind more tightly with oxygen atoms in the room, that actually lowered the chemical potential energy of the molecules, and that chemical potential energy got released as heat. Right? So similarly, these steam molecules actually have a lot of chemical potential energy. And they can release some of that energy by bonding together into a liquid. Okay, you might call it water. But those bonds are very weak. And if the individual molecules have too much internal kinetic energy, then even if they come close enough together to form a weak bond, they'll just fly apart again, right? And that's basically what steam is. Gas molecules that are moving so fast that even if they come into contact, they don't stay in contact, they just separate out again, okay? But eventually, if you lower the temperature enough to about 100 degrees Celsius or 212 Fahrenheit, then the temperature, the internal kinetic energy of these molecules is low enough that they'll kind of weakly bond together and give up some of that chemical potential energy. But the bonds are still pretty weak, and these molecules can kind of very easily temporarily break a bond with one of its neighbors and form a bond with some other neighbor, right? And that's what's happening when water is flowing around. That's why it can fill up the space of its container, right? The same thing can happen yet again if the temperature gets even lower. If the temperature gets so low that the water molecules can't even kind of temporarily break these bonds, they can release even more chemical potential energy by bonding together really stiffly into the kinds of symmetrical arrangements that we call ice, Most substances, by the way, when they transition from liquids to a solid, so you have the same collection of atoms as a liquid versus a solid, become denser. They get more compact in the solid phase. Water is one of those weird special exceptions, and that's why ice floats. The solid phase of water happens to be denser than the liquid phase of water. It's kind of a weird, atypical feature of this particular way that H2O molecules have these kind of weak hydrogen-based bonds. Okay, I want to say a little bit more about what happens when an ice cube is melting. Right? So suppose you've got an ice cube, you just pulled it out of your freezer, and you plop it into a glass of water. What's happening? At first, ice from your freezer, say from freezer, is colder than the freezing point of water. That's part of the point. So the ice from the freezer, if you have a typical freezer, is probably at say, 0 degrees Fahrenheit is a common freezer setting, and that corresponds to something like minus 18 Celsius. Okay, so what happens when you first take the ice from the freezer into the glass of water? Well, the water is at some temperature, maybe it's 5 degrees Celsius or something like that, and at first, heat flows from the hotter object to the colder object, and that goes into increasing the temperature of this ice cube, right? So, stage one, the ice warms up until it gets to its melting point, until it gets to 0 degrees Celsius or 32 degrees Fahrenheit, right? At this point, the ice does not get any warmer, right? Even though heat can still be flowing from, the outside air into the ice cube, or if the water is still at more than 0 Celsius, from the water into the ice cube, that thermal energy does not go into making the ice warmer than 0C. It goes into starting to break those stiff chemical bonds keeping ice together. And the heat that you have to use to transform a certain mass of a solid into the same mass of a liquid, even without changing the temperature, it has a name. It's called the latent heat of fusion. So stage 2, the ice starts to melt, staying at 0 degrees Celsius, and the latent heat of fusion is the thermal energy that's going into breaking the bonds, turning bits of ice into bits of water, is the thermal energy used to turn ice into water, or solid into liquid. And, sorry, that was just a timer. Great. What was I going to say? Latent heat of fusion. This can actually be a large amount of energy required. So for instance, to turn 1 kilogram of ice sitting at 0 degrees C into 1 kilogram of water, also at 0 degrees Celsius, so not changing the temperature of the system at all, just melting a kilogram of ice, requires something like 330,000 joules of energy. Okay? And if we compare that to, remember, this particular number is different for different substances, and for water, this is, the value. Recall that the specific heat of water is about 4,190 joules per kilogram per degree Kelvin. Right? It takes this many joules to heat 1 kilogram of water up by 1 degree Celsius, or by 1 degree Kelvin. Okay? So let's think about that. It takes the same amount of energy to turn a kilogram of ice at 0C to a kilogram of water at 0C as it does to take a kilogram of water at room temperature and boil it, raise the temperature by a little bit less than 80 degrees Celsius. Right? So these kind of latent heats involved in phase transitions can actually be quite large, right? And actually, a similar thing happens. For turning a liquid into a gas. Okay. So it turns out it's even harder to separate water molecules than it is to kind of break ice bonds and turn them into liquid bonds. Okay. So the latent heat of vaporization, for turning water into steam, which is the analog of this latent heat of fusion for turning a solid into a liquid. For 1 kilogram of water at the boiling point of water is 100 degrees Celsius or 212 Fahrenheit. 1 kilogram of water turning into 1 kilogram of steam, that takes some enormous amount. I always have to look this up. 2,300,000 joules, right? Just enormous, right? And that's actually why evaporative cooling can be so effective, right? Like if it's a hot day and our body is trying to cool down, that's why sweat is such a powerful evolutionary trait, right? Some moisture beads up on our skin, and then some of the excess thermal energy that our body is generating goes into, evaporating that water and having it fly off as steam into the atmosphere, right? And that can carry away a large amount of thermal energy, leaving you nicely cooler, right? I want to mention that, I talked about kind of the energy you have to pump into a system to go from a solid to a liquid, and then also from a liquid to a gas, right? The same thing happens when you're going in the other direction, right? So if you want to melt ice into water, or if you want to freeze water into ice, sorry, it's been a long day, you bring the temperature of the water down to 0 degrees Celsius, and then as you continue to remove heat from your system, you don't lower the temperature anymore at first. At first, all of the heat that you're taking out is just going into this latent heat of fusion process going in reverse. In this case, you take out heat so that you can change that kind of chemical potential energy of water going into ice or steam going into water. And so the latent heat of fusion is, for instance, the amount of heat you need to continue to remove from water at 0°C to get it to freeze into ice at 0°C. And similarly for turning steam into water. Okay. Now, one of the reasons that I wanted to take a detour and talk about this is to emphasize, these kind of large thermal energies that can be associated with phase transitions. Not associated with changing the temperature of something, but just with, getting a substance to change from a liquid to a gas, or from a gas to a liquid, or from a liquid to a solid, so on and so forth. And that principle is actually how refrigerators work. So let's talk about that in this last section of chapter 9. So this is section 9.3.2 of the lecture notes, which talks about a vapor compression refrigeration unit. Okay, so first let me take a little bit of time to draw a little schematic of a physical setup in your refrigerator. So this is not like a cycle in the same sense as when I was drawing the pressure volume diagram, but you'll see what I mean in just a moment. And this is figure 9.5 of the lecture notes if you want to follow along. Differences in the widths of these channels do not mean anything. This is just I'm a bad artist. Okay, what I've drawn here is a refrigeration cycle. So inside this continuous channel, which you should think of as like coils of metal tubing for the most part, is a refrigerant cooling substance, right? This used to be Freon. I actually don't know what it is these days. It's some substance that was selected for having particularly good thermal properties of the sort that I'll talk about in just a moment. There's going to be several kind of sections of this cycle that I want to talk about. There's kind of part A, and this is a section where some amount of heat is going to be exhausted. Great. There's going to be this part B where the tubing gets suddenly constricted. There's going to be this part C, which is where we're going to take heat from the refrigerator and put it into this coolant unit. And then there's this part D, the compressor, where we're going to have to do some work. And there's like some thermal insulation here. Thermal insulation. That is keeping a cold part of your system separate from a hot part of the system. In an actual refrigerator, the cold inside part is the inside of your refrigerator, and this hot outside part is the rest of your kitchen. Okay, and we will come back to this diagram many times. So inside these coils of tubing, there's, like I said, some refrigerant fluid chosen for its thermal properties, in particular chosen for the temperatures and the pressures at which the substance changes from a liquid to a gas and vice versa. Right? So now that I've kind of set this up, let's walk through the key components of this vapor compression cycle in the order that I've illustrated here. So part A is called the condenser. The condenser. And the condenser is typically like a winding coil. And at this part of the cycle, the fluid inside these coils is relatively warm, right? So there's like warm fluid here. And these coils, which you'll find like on the back of your refrigerator, if you ever turn it around, have a lot of surface area. So the point of this condenser is basically to dump heat into the room, right? So these winding coils full of warm fluid, warmer than the ambient temperature, let them very efficiently radiate heat away, dumping heat into the room. And as the gas in these coils is cooling down, it's condensing into a liquid phase. So over here we have hot gas kind of entering the condenser and radiating heat away and then cooling down until it becomes a fluid by the time it gets to the end of the condenser part of the cycle. Okay, so condenser radiates heat into a kitchen, condenses hot gas into warm fluid. Sounds great. Okay, part B of this cycle, part B, this place where the tubing suddenly gets very narrow, is called the expansion valve. sometimes also called the constrictor, and that's what Bloomfield's text calls it, but this is what I've always learned it as. The expansion valve. What's the point of this? So here, basically like a warm, high pressure fluid encounters a constriction. And this dramatically reduces the pressure immediately afterwards. Reduces pressure. Okay. I'll kind of talk about what that means in part C, this part of the cycle as well, right? So what happens when you dramatically reduce the pressure? Part C of this cycle is called the evaporator. So because of the lower pressure, this warmish fluid suddenly finds itself above the temperature at which it will naturally evaporate. Now, we haven't really discussed why there's a connection between the pressure of a liquid and the temperature at which it will boil, but it's true. And maybe you know this if you have ever had to think about adjusting your recipe because you're cooking at altitude. So for instance, water boils at a lower temperature in Denver than it does in Atlanta, because Denver's elevation at about a mile is much larger than Atlanta's elevation, which is only, 700 or 800 feet. And so the air pressure in Denver is much less than, or at least a little bit less than the pressure in Atlanta. It's also why pressure cookers work, right? In a pressure cooker, you increase the pressure, and that increases the temperature at which water boils. So if you have boiling water, it's at high temperature and your food cooks really quickly. Whereas at atmospheric pressure, the temperature of boiling water is just 100 degrees Celsius, and that sets the rate at which, heat can flow from boiling water into an egg or chicken or whatever you're boiling. Okay, so turning back to the refrigerator, the warm fluid, as I said, is suddenly above the temperature at which it evaporates. Okay. So great. Heat from the already cool air in the cold compartment now flows into the fluid in the evaporator, which is another set of coiling tubes, to provide that extra thermal energy we talked about to actually turn the liquid into a gas, right? So just like we talked about here, even if you have water at 100 C, it's not just going to immediately turn into gas. You still need to supply thermal energy in the form of this latent heat of vaporization. So a similar thing happens here. You've got this already warm fluid, but it's at a point in its pressure, temperature kind of phase space where it wants to turn into a steam or a gas. So it draws extra thermal energy from this already cold part of the refrigerator to make that happen. Okay, so this draws energy from a cold part of fridge to supply the latent heat of vaporization. Okay. Finally, we get to part D of this cycle, where I've drawn this kind of schematic piston, and this in a fridge is called the compressor. Okay. So at this point, we've got still a fluid, but by this point in the evaporator, it's turned into a coldish gas, right, as it's flowed from this part of the cycle down to here. Well, in order to start this cycle over again, on the left side of whatever this box is, we want to take a coldish gas and turn it into a hotish gas. This is the stage where we put work into the cycle, right? So true to its name, a compressor compresses the gas, and it does so very quickly, so that the work that we do to compress the gas goes into the internal kinetic energy of the gas in this refrigerant fluid system, right? So typically we feed in electrical energy into the compressor. The compressor does work on the incoming low density coldish gas, jamming it up into a smaller volume, and in the process increasing its temperature. Compresses the gas, increases temperature, requires us to do work. And there you have it. That's how a vapor compression refrigeration cycle works. And again, let's kind of think about this in the context of these idealized schematic diagrams we put in the first place, where we said any refrigerator, any heat pump, is basically something where you feed in work, and then as you feed in work, it takes heat from somewhere that's already cold and dumps it out into somewhere that's already warm. And that's what we're doing in this cycle. We are pumping in work at the compressor, right? So we supply work, electrical energy that runs this compressor, and what happens as a result? We take some amount of heat into this refrigerant fluid from the cold part of our fridge, and we release it back into our kitchen or vent it out into the atmosphere or something in this other part of the cycle. And there you have it.